So we have studied from the beginning of the cognitive psychology. By yesterday, we handled most of the major topics of cognitive psychology. In particular, right, all the component we have to know, like such as memory, right, visual system and auditory system, all anatomical stuff in human, the psychological aspect has been made by yesterday. So from today's onward, we will study some sort of, new area in cognitive psychology, in particular, how humans behave based on their cognitive resources. One of the main topics, one of the applications in our human cognitive resources is being used for problem solving. Okay, we know the memory, right? Some of the memory, some of the knowledge is in our brain, right? That is all we know, how to represent it, how to use it. A point about today's lecture is how humans actually use this knowledge, for problem solve. Okay, such as when you have to buy the new mobile phone, how can you find or how can you use it? How can you call to someone? Okay. So major area in this cognitive psychology is go into the problem solving, and then from now on, problem solving is pretty much major topic in human-computer interaction. You know that? Anyone knows the human-computer interaction? Probably we have a fourth year. The next year, for the fourth year students, you will take the human-computer interaction. The half of the human-computer interaction is about the problem solving. We have to represent how people solve the problem, okay? How we can help them to use some of the information we had on mobile phone or software or system to complete a particular task with the system. That is all about human-computer interaction. So we will discuss the prominent figure, Alan Newell and Paul Simon. Do you know? Simon, chapter 1. Herbert Simon, yeah. Oh, not Paul Simon, sorry. Paul Simon is, yes, I had too much drink last night, so I just mixed up with the name. Thank you for correcting me. Okay, Herbert Simon is proposed one of the major theory of problem solving called general problem solver. Okay, we will discuss something about this kind of stuff. Right, what is the problem solving then? Okay, that is what we have to deal with today and next week. The first one. Problem solving like this one. So starting from 1927, in the beginning of 20th century, we believe that only human being can solve the problem. Only human. Right? But actually in 1927's experiment, it says some of the chimpanzees can do some problem solving. Have you seen the movie, the origin of the Rise of the Planet? Rise of the Planet? The Rise of Planet of Apes. Yeah, the movie. The latest one. In that case, it's chimpanzees are using some of the drugs, okay, to improve their knowledge. But actually, the real chimpanzees do some problem solving. His name is Sultan. The picture is like this one. That is Sultan. What he did was a very simple tool, because actually they started with a small stick to find their food. But when he did the experiment, he has to use two sticks together, put them together to reach the food, right? But actually it takes time to learn these kinds of new idea. But actually the initial time is he can't find the food with this short stick, but when he put them together, he can do it. So that by the trial and errors, he did some kind of the problem solving that we only believe that human can do it. Because this experiment is so that important because human and other animals, in particular primate, can do the problem solving. Right, this one is some kind of size of our brain, but it's not the real size. It's not the real size. Our brain is much bigger than chimpanzees, but we just put them together, these 6 brain, into this picture. So when you look at this one, so many of the monkeys and cat, the most important part of the human problem solving is frontal area. In Korean, it's 전두엽. Okay? So in this area, it's very important for the problem solving. So when you look at this one, human being, pretty much major part of the front side is being used for problem solving. So we had some, dog is very small area. Chimpanzee is quite a similar size, similar area of the using from our frontal area, frontal cortex. However, our brain is much bigger than chimpanzees. Okay? So that is Sultan. So our first time, okay? Right, that is important part of our problem solving. So when we do some problem solving, that is a major part. So we are goal directedness. That is, who made it? Who firstly proposed that we had a goal directedness? Who? Youngjin? Simon, okay? The Herbert Simon and Alan Newell, when he proposed the first idea about human problem solving is we have a goal directedness. These kinds of things, I mean, the first principle about the problems of goal directedness is being attacked by many of the researchers. Say sometimes we may not have any goal, but basically all the problem solving need a goal. Say like the want or the need. So because you're hungry, you go to the shop to buy something, right? So all the human need a goal to start with. Yeah, that is a major part of, though we have goal, so we need a goal. And when we have a goal, in particular complex goal, we have to divide and conquer. Okay? We have to separate them out with the easy part. That is called the sub-goals. Okay? And then when we have a tangible and manageable sub-goals, and then we can select action. Okay? When you have a goal, and then we have a selectable actions. This one is a major part of the human-computer interaction to design procedure. Right? So, any task. Any task. What do you want to do with the mobile phone? Send a text message? Okay, so that is your goal. Okay, how can you send a text message? How? So that is a major goal. Now you have to divide and conquer, right? You have to make sub-goal decomposition. Okay, am I right? Sub-goal. What is sub-goal? Anything? Oh, okay. So if you want to send a text message, you have to, okay. Okay. You have to find the mobile phone. And then? Turn on the mobile phone, okay? Turn on? Okay. That's it? Anything else? Touch. Okay, so probably we can rewrite what just Yongjun said is find an icon. Something? Find the icon? Am I right? Yeah? Okay. Find the function is better. Okay, find the function. N. Huh? Type. Okay. Find phone. type or edit. And maybe we have to do check the messages. You're not checking the messages before you sending? No? No checking? I have to check it, otherwise. Okay, check the messages. And finally, we can send it off. Of course, this kind of subgoal decomposition is pretty much automatic because say it again. Yes, we have what? Expertise. Technically saying, we have expertise, right? Because we know everything. Smart, right? So this one is pretty much automatic because we have expertise. As you know, this one is very simple sub-goal decomposition. But actually, when we do some study about problem solving, many of using these kinds of procedure. And then, so that is a major goal and sub-goals. Now you have to decide what action. So this one is your goal. And then when you have a goal, next one is what? You have to action. Okay? What action? To achieve this sub-goal. What action? Okay? That is your action. Right? You have to visually search it. Or you can use other phone to call them. To use, do you know what I'm saying? If you can't find your mobile phone, you can just, in your home, so you can just using your mom's mobile phone to call it, to hear, right? So we can use what? Audio search or audio hint. Okay, turn on mobile phone. How? Action. Hold down the button. Oh, what is it? How do you turn on the mobile phone? Hold down. Hold down the button or what? How can you turn it on? Just always on? Huh? Click what? Click the button? Everything, all the action is click. Click. Well, hold down the button or something like that. Hold down the button or key, or as Yongjun say, click the button. Find the function. How to find the function? How? Visual search? Okay. Edit. Motor skill? Okay. Okay. Check the messages. Visual channel. Okay, using the visual channel, send it off. Action is another click. Okay, this time. Okay, click. Right. So for the goal achievement, we made 6 sub-goals and then we defined the action. That is how we solve the problem of send the text messages. Right? So that is what Herbert Simon and Alan Yo made his first model of processor, the general problem solver. Based on this one, they made the first AI model, artificial intelligence application. Of course, this approach is being used product design, like human-computer interaction. So when you analyze the goal, the task, so if you're the designer of mobile phone, okay, just believe that, imagine that. You are the mobile phone designer. You have to make a procedure, right? So that is goal. You want to make this task to help people. You have to make this kind of sub-goal decomposition, right? And then each of them must be designed on your mobile phone, in particular supporting the action. So for example, if such as this one. That is the design moment, the moment of the design. Okay? So how? This action is the only one? Is a unique one? The designer can make a new action. The point is, people has to know whether this action can achieve this sub-goal. So for example, if Yongjun made, like this one is mobile phone, what Yongjun made, the button is in here, and that is display. If your design, the Yongjun's design doesn't support whether this one looks like power button or anything else, people cannot recognize it, so they just say, they just always complain about where is power button. Isn't it? That is your degree of freedom, your freedom to design anything, but point about in design exercise is you can make any types of action support, but you just must know what you have made to achieve this sub-goal. Okay? In that case, we can, like this one, like if it like, sorry, if you just make it bigger, magnify it, like this one. Okay? I or P, right? So if you make it, people can, okay, that looks like power button, right? And then they just click it. If there is no responding, okay, they will hold down this button for the long time, couple of seconds. That's we already know, hold it down the button. So likewise, this system design, that is one you have designed, and this one has a system effect. Okay? As a designer, you can control this part. As an information designer, you can control this part and this part. Action selection. However, you cannot control the sub-goals. You cannot. The only way you can control the sub-goal decomposition is like a wizard application. If you make a wizard application, do you know chart wizard or the word art wizard? You can just simply click next, 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 right? When you use the software with the next button. So that already gives you the sub-goal decomposition. Designer can make this sub-goal decomposition with like a wizard application, but in most cases, you cannot control the sub-goal construction and elimination with the system effect. Okay? So that is how it works. That is how this problem solving is linked with the human-computer interaction, in particular, the procedure design or system effect design. Right. So that is how three features of problem solving is. We have goal and sub-goal decomposition, and then action selection. Right. Hey. Right. So Alan Newell, Herbert Simon, they made the first HCI model called GOMS. Goal, operators, method, and selection rules. Like this one. Okay, that is a different application and different problems, but it looks like likewise we have goal, sub-goal, and operators. Using this very simple model, they can make first HCI model called goal, operators, method, and selection rule. Okay. Right. Now, you have to remember this one, the GOMS, very popular, but it's not much being used at this time because there's really old classic model. Nobody used the GOMS yet, but traditionally that gives us very intrinsic aspect of the knowledge representation or problem-solving approach with goal, sub-goal decompositions. Okay, that's what I want to say from in here. Right, to make these kinds of goal, sub-goal decomposition, we have to make problem space and state. Okay, in that case, when you have these kinds of problem space, as a designer, as an information designer, you have to define the state. Where you are and where the system is. Like in here, like in particular this one, turn on mobile phone. Okay, that is display. Okay, probably in here we have some kind of standing. Why you laughing? No? Oh, okay. So this one is standby mode. Okay. Okay, and then that is what Yongjun's made the power button here, right? That is initial state. Okay, and then when you have to design as information designers, when someone hold down these buttons, you can make what? New system state. I'm not good at drawer, but I mean something. Okay, LG. Something about the flashing the images. When you hold down the button, when the power on, something comes up, right? And the gun suddenly, right? So that is kind of, okay, the state 1. Okay, from the state 0, standby state, we can call this one state 0. And then you can design to make a state 1 to move into by the action. Okay? Action is what? This one. Hold down the button. Okay? And then what you can do is, what human beings do is, they are evaluating this state 1. Okay? Because they was in state 0, and then they take the action, hold down the button, and we see some of the flashing, the display. With the state 1, we evaluate whether this one completed or not. Is it completed? Yeah? When you see this state 1, we can say, oh, subgoal 1 is completed. Subgoal 2 is gone. So then we can carry on subgoal 3. Until we finish this one, we can't do this one. That is all the AI logics doing it. But human has a little bit different approach. We can jump between them, but not in this example. But in many situations, the computer only can do some kind of production system like this one. They have to meet one of the sub-goals and then go to the next goal. A human can jump around between the sub-goals. So AI exactly not to meet our human problem solving, but that is a very traditional approach to decide how you can make a system state to let them know, let the user know whether they have completed sub-goals or not. So that's the why in this slide is explained that is whole the problem space, what we have, and then each of the time, each of the state, For each of the stage, we have to make state representation, like what I did. I'm just using state representation with a picture, like this one. Some people use a production rule. Some people can use the probability, okay? But I mean, or description, or text, whatever they want. But so there is a heaps of different types of the representing the state. Okay, start state is state 0, and then goal state is when this one. Goal state means the final state. So in here, okay, when you send it off, and then most of the mobile phone is coming back to the initial state, isn't it? Standby mode. Okay? So that is when we have this kinds of state 0 on my mobile phone, we believe that we completed goal. Or there is some kind of feedback, such as, yeah, done something, or your request is completed, or your message has been sent. Okay? Something like final message. When you see this one, oh, now I complete the super goal, the top goal. Okay, the main goal, not sub goals. And another things, okay, for this one, each of the sub goal also has sub goal decompositions, right? Goal, sub goal, sub goal, sub goal, right? There's heaps of goals. But this one is very simple logic. For the only we have one level of the sub goal. But in many cases in human problem solving, when you draw this one like a hierarchical structure, that is super goal, and that is sub goal, And to achieve each of the sub-goal, we can have another sub-goal. Likewise, these kinds of the goal structure is possible. So when you need to analyze your mobile phone to make a new mobile phone, we have these kinds of really long list of the hierarchical structure, right? Okay, but that is not that important at this time, right? When you have all the problem space is made, right? Now people seems to trying to search all the state. The idea about this one, the traditional AI is we defined all the system state, and then some of the logic is find the best way. We are not sure about whether people are using these kinds of things. That's why the problem solving research is trying to find the empirical evidence whether we do the same thing like computer. Okay, so idea is this one. This one, say like when you have a state definition like this one, all the state, okay, and then people trying to search it. You never know what I'm trying to say. Okay, I will show that. Like this one. So our goal, that is current state, start state, and that is our final goal. You know that the block moving around, the tiling moving around the tiles, right? This one is this one. So how people can do this one? From here to the final goal state. So that's the why the older problem solving approach is made like that, right? To achieve this goal state, we have, people have a different state. That is one of the answer, one of the problem solving strategies. So it takes 27 steps. Am I right? 27? 2, 4, 6, 7. 27 times 4 is 27. Yeah, 27. I'm really bad at math. Okay, so we need a 27 state. Okay? In each of the time. So that's how human problem solving approach from the A to the final. Okay? So that is one of the answer, but we have to understand whether this one is only way we can achieve the goal state or not. We have different answer, much different answers depending on who you are. For me, I never completed this goal state. I really hated this game, but most of you can do this one much quickly. Right? The idea about this one is how we do it. So, the researchers believe if we represent all the state like what we did just before, is people trying to search the best one in each state, right? You get it? Okay? Makes sense? Common sense, right? Huh? So we have to search it. Otherwise, we can't find the goal state. Okay? So, that is one. Okay, just move it. From the start state, okay, that is from here to in here, how we can, we have goal state in here, in any way, so we have to moving around for each step to find the better answer. Okay? Step by step, in piecemeal way. Right? So that's why we have to starting, okay, 4 is moving to in here, something. Every time we take the next action based on the current state to improve our answer. Right? That is human behavior. We never backward. We go forward. Right? Can we show that? Okay, that is another thing. That is how we can represent in the goal structure like this one. Right? So that's how we do this one. So I can make 5 different strategies how people are problem solving, solving the problem. First one is trial and error. How many people are reading a manual when you buy the new mobile phone or new system? Anyone read it? But why we need the instruction? Huh? Why we need the instruction, manual? You never read it, right? Anyone read? I found a couple of people when they buy the new system. You read it. Beauty. From the first page to the end. Of course, yeah. So some people are reading it, but most of us is simply do trial and errors. And then while this exercise, we come to know how to use it. That is human. Okay? Have you heard about machine learning? Machine learning system? So in the AI, in artificial intelligence, okay, the sum of the application is keep learning with the trial. Okay? So they improve their machine knowledge. Okay? Otherwise, we have to program in every rules, but we can't do it. That's why we just make the machine learn himself or learn itself, okay, to improve their knowledge. So there is another technique, it's called machine learning. Okay? So that is how we do it. And best one. Somebody let you know, like teacher or mom or daddy. Normally daddies, yeah, they never teach anything. But mom did it. Okay, so, and the society let you know how to solve the problem. Society. So that is how the Bandura is called the social learning theory. People learn something from the society. If you live alone in some isolated island, you never learn anything. Right? Because society cannot give you any answers or any problem solving approach. Okay? And then very useful thing is example. So if I let you know some of the example, okay, like this one. Right, this one. This one is instruction, and this one is how to solve the problem like a pyramid expression. They made a pyramid expression like this one. $7 means they just adding up the other 3-digit number. Okay, so 654. So if I give you some kind of example like this one, much faster than read this instruction, isn't it? So that's how we learn by example. And another things, okay, this one, analogy. We solve the problem using analogy. So why atomic scale, atomic structure? Atomic structure, you know the atom, 원자 구조, atomic structure, right? So, what is in the center? Nucleus. Am I right? Nucleus. Physics, basic stuff. Nucleus, okay? Proton and neutron, everything in here. And then, what is it? The side one. Electron, right? So, when this one identified? In 1940s, 1920, 1930, right? At that time, we don't have the microscope to see the atomic structure. But how people believe that this looks like that. Atomic structure. We copied it from solar system. We copied it. Solar system. We have sun. Okay, we have the Mercury and Venus, that sort of thing. At that time, people believed that we can't see it, but probably the atomic structure looks like our solar system. So the best approach in many cases, okay, or creative idea is using the analogy. Desktop interface. We call the Windows system is desktop interface, right? We have trash bin, 휴지통, trash bin, okay, and file structure, cabinet. Where we get it? We just copied from office environment. So that's why we call desktop environment. Eraser, right? File open. Okay, everything copied from the real world. So that is analogy. Okay? So analogy is really powerful, and then some of the experiment is also proved that people using analogy. Such as this example, when you read a very long text in chapter 8, so I can't, the typing, because I made this slide in a couple of hours ago, so I don't have time to type everything. But when I read this one, say like, that is cancer treatment problem, right? That is really hard problem, but when people is being given by the sum of the analogical problem, redefine it, okay, they can easily access to find the answer. Okay, this one is a really difficult problem, but we can redesign with a much simpler problem with analogy, like 4 trees. Okay, I mean, you read it, you can understand what I'm talking about in chapter 8. Right. Problems about analogy? Analogy has a problem. Analogy is a really powerful tool to problem solve, but there is a limitation. Big limitation, big drawback. Is in here? Oh, yeah. That is all the good things. But there is one major problem of analogy. Huh? What is it? What do you think? Analogy? Problem of analogy? Nobody knows?
Different high speed length.
Oh, yes, I know what you're talking about, but that is the right answer, right? So the problem of analogy is when you're trying to transfer one experience into another, it doesn't the same thing. It's not the same thing, but we just believe there could be similar answer. So when you find the answer based on analogy, it might be the right answer. That is only when you believe the right answer using the analogy, but actually it is the different problem solving approach. Okay, so the analogy, you have to be very careful to say whether this one is right or wrong at the end. Otherwise, you may end up with the wrong answer. Very long answer. That is a major problem in analogy, so our textbook doesn't say. So, yeah, that is how our system, solar system atomic analogy. Okay. From now on is the major part of problem solving, and that is human problem behavior, solving behavior. Okay. We have 3 major things. So that's the major thing of the chapter 8. So only 3 things you have to remember in chapter 8 is these 3 things. The first one is backup avoidance. We never go back. We keep forward. Keep go forward. Okay? The idea is this one. Okay, for the problem solving in our human behavior, that's why human cannot find the optimal solution sometimes. Computer can do it. Right? You have to exactly know what's the difference between human and computer, like this way. Okay, I can make a structure. Okay, imaginary structure. Okay, goal state. Okay. So, for example, okay, that is number 1. Okay, 2, 3, 4, 5, 6. Okay. So when you have this kind of state definition like this one, the first one say backup avoidance, right? This one. So when you start with this one, what do you want to choose? They are comparing it, right? So they have to go in anywhere in here, right? But people trying to find, well, better answer, right? So if this one is like a, okay, number, okay, number. Okay, that is plus 10. Okay, that is minus 10. What do you want to choose? Yeah. Right? And then, okay. Okay, so like this one. Minus 10. Which one? Huh? Oh, plus 10, right? You go this way, right? However, we may have a 100 in here.
그래서 마이너스 10.
Okay. Anyway, so that is an example of backup avoidance. Okay, we just go compare the next step, whether they can give us better answer, we choose it. We do this one, but computers can avoid these kinds of problems. They search all the space to find the global optimal. Huh? Human cannot do it. We just stop it in here. Oh, yes, we have we are satisfied because we have 20 increased at the end. Okay, very similar example. The super goal kill-off is this one. Okay, that is a very traditional human errors like this way. ATM machine. ATM, many of you already use how to use the ATM. Insert card, and then withdraw money, right? And then what? What is the procedure? Insert card and specify the amount of money, and then take out the money? Huh?
Password.
Huh? Password, okay, password, and then? Card first or money first? Oh, why card first? If the other way around, what would happen? Oh, yeah, forget the card because you already achieved the goal, right? That's the why ATM is always a card first and then money later. Huh? And by 1990s, we had that kind of ATM machine. We do. In America in particular, and I've been there in Chicago, there is that kind of money and then card, so that there's heaps of card lost around there. So likewise, the super goal kill-off means when we achieve the final goal, we eliminate most of the sub-goals. Huh? That is called the backup avoidance and super goal kill-off. Right. And then difference reduction. Yes. Okay, and difference reduction means people do find the answers based on the difference, state difference, and then they try to find the bigger difference, close to the goal. Okay, idea is this one. Okay, that is 10, that is plus 10, plus 20, okay? This one is not a good example. Hey. In this case, which one do you want to choose? The 20, because that is close to your goal state. Your goal state means the maximum profit, such as. If your goal is maximum profit, we choose this one rather than these two, because that is close to the goal state, right? So I will give an example in here, okay, like difference reduction, hill climbing, like this way. So that is our textbook. Our textbook example say our main goal is this one. We have 8 liters of waters in jar A, and the B jar and C container doesn't have any water. Our final goal is like 4 and 4. We have half the 4 liters in cup A, 4 liters in another cup B, right? That is our goal. So that is describing how we do it. Say, okay, that is the first time they have to move 3 liters into the cup C, okay, and then the cup C, the waters in the cup C and the cup B, right? Likewise, that is goal state. They define the 14 different goal state and the state representation. Idea is this one. Whether people choose this one or this one at the initial action. Huh? Right? Okay, this action is we can put 3 liters into cup C, and this one is we can put 3 liters and put the 5 liters in cup B. Why we choose the B? Yeah, because that is close to the goal. So they made an experiment with heaps of people, whether people choose this one or this one, which one is more preferred. We found that this one is much preferred because that is close to the goal. We always compare, that is goal, and the next action must be getting closer to the final goal. Okay? And then we never get back. We never give up. So keep going on to find the best answer in every action step. We never go back. Okay? That is a human limitation. Computer can go back to find the optimal solution, but human is not much like that. Okay, that is meaning of the difference reduction method. Okay, so people experience difficulty in solving a problem at a point where the correct solution involves increasing the difference between the current state and goal state. That's why people has a very difficult to process some of the problems. That is what Alan Newell and Herbert Simon made an approach called general problem solver with the means ends analysis. Okay, what is the back of avoidance and the difference reduction method? That is the major approach how humans do it. But means ends analysis, we are not doing much. Human is not doing the means ends analysis much. So what Herbert Simon and Alan Newell made is this one. Okay, they describe all the goal state. Okay, all the state. Okay, they defined all the state of the problem and like this one. That is GPS model. General problem solver, what Herbert Simon and Alan Newell made. Okay, this one. They define all the state and the means ends analysis is trying to find the right answer. Search everything. Basic idea, search everything. But how to search it? That is what the GPS has. Okay, step by step, I can explain it. Okay, major idea is that. Okay, Herbert Simon and Alan Newell, first in our human history, human knowledge, okay, they made a general problem solver in artificial intelligence. Okay, first AI model. Problem solving simulator, models human problem solving using means ends analysis like this one. Okay, so that is basic idea. We human being is trying to find the next goal with the difference detection. When you find that we haven't reached the final goal or the destination, we detect the differences. So when we detect the differences, we just trying to do something, right? That is we doing the sub-goal decomposition, right? So if that is fail and they're successful, they can just reach to the final goal. So this idea is keep we doing this kind of process. Okay, search for the operator, and operator found and match the condition. When we reach the sub goal or not is using this kind of flow chart to solving the problem. And means ends analysis is involving the creating sub goal to eliminate the difference between the current state and the condition for applying the desired operator. Basic idea is this one. More sophisticated version of difference reduction, but means ends analysis is search everything. Here, does not abandon an operator if it cannot be applied immediately. Difference reduction method, in that case, people are giving up in some state like this way. That is 20, but so, for example, that is 1,000. Okay? The 10,000 in here. But when we decide the difference reduction method, when we not decide this one, all the branch is gone. Okay? We never searched it. But means analysis, no, we have to search everything. We have to define all the world state and then search it. So that is only difference. So the first AI model is better than human problem solving because of that one. People normally discard some part of the branches or some part of the goal state, but means ends analysis, oh no, we have to search everything. So do everything search. So, Tower of Hanoi. Have you heard? Huh? You know what is the Tower of Hanoi? Okay, let me show some of the video clip. That is moving around. So we have 4 stacks there. So to solve the problem, we have heaps of steps like that. So that is when you see the movie, The Rise of the Planet of Apes, right? In that case, the monkey, the chimpanzee, is doing these Tower of Hanoi games. In the very first thought, the first part of it, keep doing it, isn't it? So idea is the bigger stack cannot go to the top one. Right? That is Tower of Hanoi. And Alan Newell and Herbert Simon involving the moving disk among the packs, and Tower of Hanoi problem is solved by adapting means and strategies in which sub-goals are created. Which means, for the solving these Tower of Hanoi problems, the difference reduction method is not much helpful because people is stuck in some state. But when you do the GPS, the means engine analysis, we just state everything. Okay, state everything, right? And then search every part means we can solve these issues with the means engine analysis. That's why Tower of Hanoi is kind of detecting whether people can have a high intelligence or problem solving approach. Like this one is Tower of Hanoi. GPS firstly applied Tower of Hanoi. That's why this Tower of Hanoi problem is popular in problem solving domain because GPS firstly applied to solve this Tower of Hanoi problem. That's it. That is what I have prepared for today's lecture. And then from tomorrow, next week, I'm just explain the rest of the problem solving and decision making process in next Wednesday. Right. Any questions? No. I finished it. Okay.